we have a temperature which is, I don't know, more or less 900. If I use the same process but with a different power, I stop here with a double of power. I can reach the same layer of transformation, but with the shortest time in comparison with this one. But if I evaluate the surface temperature, it will be much higher.
Okay. So we move on the C equals 1 to see the surface temperature, and we move
Yes.
again.
So if I would like to have a transformation of a big layer, I stop here, for example, 70%. I'm here, and then maybe I have much more. Why? Because I'm giving a lot of power for a longer time in order to reach the layer.
It's possible to change properly the power used for
This is the reason. By this way, we are designing the process. But the idea that I would like to give you is that we are free to choose different parameters. And these are only two, because we have fixed the value of n. But then we can use also the parameter n. So we have at least three parameters: power, time, and n. Power, time, frequency.
They use a low parameter of n because it is quite easy to manage the temperature through the layer instead of having a exponential
No. Frequency means that I move the distribution more or less to the surface of the piece. More or less. In any case, we have a shallow distribution of the density. But it will be much or more or less shallow. So, you have the freedom to choose such kind of parameters by this way, only using such a kind of diagram, which is the solution of the Fourier equation that we see just 3, 4, 5 minutes ago. 20, half an hour or so. Okay? But these are only electromagnetic phenomena. So let me say that we are freezing the power density distribution. But the heat transfer phenomena works in a better direction. Why? We can see from this slide what I mean. So, this is the prescribed case depth, the prescribed hardened layer. Okay? So we have fixed from the diagram of the previous slide the thickness, and then we have this distribution. But you know, this is what's happened when we stop to heat. Zero. It means at the 0 seconds, so when we have stopped to heat, we have such a kind of temperature distribution. Okay? Now, I'm switching off the generator. What's happening?
soaking effect.
Yes. The soaking effect in two directions. The first one, inwards the center of the billet. There is a heat diffusion towards the center of the billet. The second one is a bigger cooling of the surface. So it means that if you look at the second number one, the red one, there is an immediate moving of the heating front towards the center of the billet, the red one, but at the same time a cooling of the surface. So it means that, first of all, if we fix 20% of the layer from starting from the surface, we could have much more layers transformed into austenite because there is a diffusion. On the other hand, even if from the diagram of the previous line we reach a higher temperature for the surface, we will be sure that this is only a theoretical value because maybe we are not able to reach such a kind of temperature for a longer time. Okay, so we don't have the possibility to have, because you know, the dimension, the size, the dimension of the grains depends not only on the temperature but also on the time that you give the temperature. So if you have only for a short time the overcoming of the critical temperature, in any case you don't have an immediate increasing of the size of the grain. You are not weakening your material in any case. You know that these aspects are not cannot be solved by theory. There is a lot of experimental tests to do. There are a lot of experimental tests. So, this is what's happening. And this is the, let me say, the summary of the procedure that we have applied in the previous slide. So, if we do such a kind of procedure for a lot of parameters, we are able to draw such a kind of abaci. This is the depth. This is the P0, which is the same, you know. We have the power per unit length, but we can give also the power per unit surface. You remember P0, you remember? You remember? So we can use also this formula. So, we can draw such a kind of diagrams. Each point of this diagram is obtained by using the same procedure like in the previous line. I use the power, I understand what is the layer that I need to transform, then I calculate the surface temperature, and then coming back. For each point, I did this procedure. So, what we can see from these diagrams? I started from the layer of the billet that I would like to harden. And then I can choose different parameters. For example, 3 millimeters. I can stop here. What does it mean? I have a specific power that I have to use for the process. I have a specific time, which is 4 seconds. And I know that I will reach a specific surface temperature. These diagrams are obtained for a specific AC3 temperature for a specific diameter of the billet and for a specific frequency. Okay? This is a very useful abacus.
But they aren't the same material.
Same material, yes.
Why the temperature? AC3 in both cases, I don't.
AC3 is the same, we are changing only the diameter.
Okay.
So these are some useful diagrams that can be used for the design properly of the parameters to be chosen for the hardening process. Nowadays, maybe these diagrams can be obtained using numerical methods. But you know, it's a lot of calculation. If you have these diagrams, 2 minutes, and you can understand what are the main parameters for your process. Because if you choose a P0 equal to 1, maybe you know the characteristics of your material because you have fixed the frequency, you know what is M, and then you are able to calculate B, and then you calculate the H0. H0 means means currents, and means number of turns. Okay?
Excuse me, but
These are other examples for a different frequency and for different diameters of the building.
this formula works only on the cylindrical billet.
Yeah.
Not
We are,
for
speaking,
other
we
shape.
are speaking about the cylindrical pillar. Usually when you have to, it's the most used geometry for shafts, for other components and so on.
Or railroad.
It's different, but in any case you can use more or less the same formulas because it's like a sort of a. So when we speak about hardening, surface hardening, we are dealing with a very small layer. Small layer means that it's quite an infinity plan.